What's up? My name is Matthew, and in this video we're going to talk about systems of nonlinear equations in two variables. And in the previous section we used primarily elimination when we came to the point where we had to be solving systems of equations, and in this section we're definitely going to use both the substitution technique and the addition or elimination technique as we work through these slightly unusual systems of equations. And if there's one mistake that I feel like is most frequently made when working with systems of nonlinear equations, it is remembering, or I suppose forgetting is the mistake, that when you take the square root of something, you end up with plus or minus. For example, the square root of 9 is positive and negative 3. So don't forget your pluses or minuses. Let's go see some examples. What we're seeing here is just a little information, generally speaking, about what it is that we're getting ourselves into as we talk about systems of nonlinear equations. And you should feel free to look through and read through as much of this as you would like. The solution set is going to be a set of ordered pairs. Nonlinear equations can still be graphed. They are not necessarily functions. We might be looking at parabolas or circles or really any kind of a shape other than a line. And in our first example problem, very conveniently we're being told to solve using the substitution method, and really the elimination method, I would say, isn't really even an option. There's no way that you could add or subtract these equations from each other in order to eliminate a variable or a term, because you don't have any like terms. We've got an x to the second power, an x to the first power, a y to the second power, a y to the first power. None of those are like terms, so there's no adding or subtracting those to or from each other. So let's go ahead and start modifying this and making it workable. I'm going to call these equations 1 and 2 as usual, and I'm going to start out by taking equation 2 and solving it for y. Let's make it say y equals. I guess I'll work my way vertically down the page here. I will subtract 3x from both sides. That's still equation 2. And then I'll multiply the entire equation by -1. And if you want to put the typical little annotations off to the side, you can. We subtracted 3x from both sides of that equation, and we multiplied both sides of the equation by -1 in order to get to where we are now. And now I'd like to take this version of equation 2 and substitute it into equation 1. And I should have turned my sound off. Awkward. All right, when we plug this equation into number 1, here's the result. The x squared stays the same from equation number 1, plus, and now we're not squaring y, we're squaring 3x minus 5. And that is still equal to 5 on the right-hand side of equation 1. And next, we need to do some multiplication. Now remember, 3x minus 5 squared does not mean you can square the 3x and square the 5. You have to actually FOIL this out and combine like terms. And if you need to write this as 3x minus 5 times 3x minus 5 and FOIL it out and draw your rainbows and so on and combine like terms, you should do that. I'm not going to do that, but you should do that and then check and make sure you get what I get, which is a 9x squared minus 15x makes minus 30x, and then -5 times -5 makes a positive 25. Still have a 5 on the right-hand side. This is still equation number 1. And now let's combine like terms. CLT. I now have 10x squared minus 30x. And I've got a plus 25, and then there's that 5 on the right-hand side, so I'm also going to subtract 5 from both sides of my equation. That leaves me with a plus 20 equals 0. You can keep labeling this equation 1 if you like. And now, in order to make my numbers a little bit smaller, very conveniently, all 3 of those numbers are multiples of 10, so I can divide my entire equation by 10. And we're working with x squared minus 3x plus 2 equals 0. In order to find the x values that make this true, let's factor. We get x minus 2 times x minus 1 is equal to 0. The x values that make that true are x equals positive 2 and x equals positive 1. Now we're making some progress. In order to find the y values that go along with these x values, I have some options, a couple anyway. I can take my x values and plug them into equation number 2, or I could take them and plug them into equation number 1. Now, how do I choose what to do? Something that you might consider doing is going into a graphing utility, in particular, an online utility like Desmos.com would be beneficial because you could type these 2 equations in exactly as they appear and see what it is that you're going to run into. Equation number 1 is the equation of a circle centered at the origin with a radius square root of 5. And equation number 2 is a line. So what should, there are some options. Either your circle is going to be bypassed by the line, 3x minus 5. Either it's going to be bypassed by the line, or the line is going to just barely touch the circle at one point, or the line is going to cross through the circle and you're going to have 2 points of intersection. I hid that behind me, sorry. So those are the 3 possibilities in this system. No solution, 0 solutions, 1 solution, or 2 solutions. Since we have 2 x coordinates, I'm guessing that we have 2 solutions. I don't think I want to confuse the matter by taking my x values and plugging them into equation 1, because it's going to generate multiple y values because of the square root property. So I think what I'm going to do in this case is I'm going to plug into equation 2 and just go right at my 2 solutions. So let's do that. I guess I'll move into this left-hand space here. It's a little unusual the way these notes are laid out. So into equation 2, we've got 3 times our new x value of 2 minus our unknown y value. Actually, instead of doing that, which you could do, what I'm going to do is I'm going to come over here and I'm going to put a star next to this y equals equation. That's a modified version of equation 2, and if we plug our x values into that, it's going to deliver us very quickly to the corresponding y values. So let's write sub into star. All right, so we've got y equals 3 times the x value of 2 minus 5. So we have a y value of 1. In other words, that's an arrow. Our x value of 2 has a corresponding y value of 1. This is going to be one of our solutions. And then let's plug in our x value of 1. We have y equals 3 times the x value of 1 minus 5. That's 3 minus 5, which is negative 2. So our x value of 1 had a corresponding y value of negative 2. This is our other solution. So your answer to this problem is probably going to be If you're entering these online as a free response solution, it's probably going to be a set of ordered pairs, so your actual solution might be in set braces, and then parentheses 2, +1, comma, 1, -2. That's my guess at how you're typing in your final answer. All right, so our first example of working a system of nonlinear equations, one of them was linear, one of them was nonlinear. And being mindful of what potential outcomes you could have based on thinking of the system of equations graphically, because one way to interpret what you're doing here is you're finding the points of intersection between the graphs of these two equations. Notice I didn't say these two functions. Equation number 2 is a function. Equation number 1 is not a function. It does not pass the vertical line test. All right, let's keep going and see what else we run into. The process was very similar to solving a system of linear equations, except once we had our equation written in terms of one variable, we were working with a nonlinear equation. It looked like a quadratic in the previous problem. Where is it? Right here. It was at this point where we really saw it as a nonlinear equation, but it was right after our substitution that we first saw that x squared and the x to the first power in the parentheses there. That's when it became very apparent that we were going to have more than one solution, probably. So here's an example where we can use the addition or elimination method. Let's try this one, labeling as equation 1 and equation 2, and I'm going to take equation 2 and multiply it by -2. So let's do that. Multiply by -2. That gives us -4x squared plus 2y squared equals +4. That's equation 2 still. And then equation number 1, I'm just going to write it down right below it. 3x squared minus 2y squared equals -5. That's equation 1. And then let's add those equations together in order to eliminate our y terms. We get -x squared equals -1. Multiply both sides of that equation by -1 times -1. There we go. Now we've got x squared equals 1. And if we take the square root of both sides, we find that x equals, and what's the square root of 1? Now you immediately thought 1, but then I stayed paused for a second there, giving you the opportunity to think of the other answer. Don't forget that when you're taking the square root of a number like this, the answer is plus or minus. I don't care if it's the square root of 1, the square root of 9 I said earlier is plus or minus 3. If this was the square root of 5, the answer would be plus or minus the square root of 5. So I don't really care what you're taking the square root of on the right-hand side. Don't forget your plus or minus. So there is our plus or minus 1. And now I wonder if you know what these two equations 1 and 2, if we graphed them, what would they look like? And this might be a nice opportunity for you to go over and jump into a graphing utility and check these out. I'm pretty sure that the graph of these are hyperbolas. Pretty sure. And a hyperbola is a graph that has sort of a sideways facing parabola in one direction accompanied by another sideways facing parabola in the other direction, and they should be even. And tilt them, there we go. So go ahead and check those out and realize that if that's what these really are, man, there are a lot of different ways. So this is one hyperbola. I've drawn it behind my head again. Scoot that down. There we go. That's one hyperbola. And another hyperbola could... So our x squareds and our y squareds are separated by a minus sign, so the concavity of these hyperbolas, I believe they are, should be going in the same direction. It could be that they don't intersect at all. We have no solution. It could be that they intersect just at that sort of vertex, and then the other one comes in and just at this vertex, maybe we've got 2 points of intersection. It could be that the hyperbola comes in like this and like this, right? So now we've got 4 points of intersection. So we've got some different ways that this could go, but so far it's looking like 0, 2, or 4 solutions. Let's keep going and find out. Whoop, put that back. Okay, let's take our x values and plug them into, I don't know, equation number 2. It doesn't matter, you can plug them into whichever equation you want. Let's try to keep this all on the screen. There we go. So going for our x value of positive 1, we've got 2 times 1 squared minus y squared equals negative 2. That's equation 2. And if we subtract 2 from both sides, then we have negative y squared equals negative 4. And if we multiply both sides by negative 1, we have y squared equals positive 4. And then if we take the square root of both sides, what's the square root of 4? Did you remember the plus or minus this time? Don't forget that plus or minus. So it's plus or minus 2. Now this is interesting. What this tells us is that with an x value of 1, which is what we started with, we had a y value of 2, and with an x value of 1, we also got a corresponding y value of negative 2. So these are 2 of our solutions, and now we have to plug in our other x value of negative 1. So 2 times negative 1 squared minus y squared equals negative 2, and that's equation 2 that I've substituted my x value of negative 1 into. And of course, negative 1 squared is positive 1, times 2 makes that a 2 again, and I'm going to take this 2 and I'm going to subtract it from both sides of my equation, just like I did previously. Can I get rid of that also? Good. All right, so we've got negative y squared equals negative 4 again, because we subtracted 2 from both sides. And if we follow that through, we're going to end up with this y value of plus or minus 2 again. And of course, these two y values are associated with, or are the corresponding y values for our x value of negative 1. So negative 1, positive 2, and negative 1, negative 2. So our answer for this system of nonlinear equations has 4 solutions, and you may again want to be submitting your answer as a set of ordered pairs, separating each ordered pair, or separating the ordered pairs by commas. So generally speaking, which method do we think that we should use in order to solve this system of equations? I'll give you a hint. It's similar to the first one that we worked with. You don't have any like terms. There's no way to get our x squareds to cancel out here, because one of those is an x squared and one of them is an x to the first power. There's no way to get our y squared or y terms to cancel out, because we've only got one of each there also. So this is another example of where you would take equation 2, solve it for y, and substitute it into equation 1. So substitution is the plan of attack for a system of equations like that one. Now, when it comes time to studying to take a quiz or a test on systems of nonlinear equations, realize that there are the 2 different methods. So you've got substitution and addition, and maybe make up a couple of index cards or flashcards or however you want to do it in order to quiz yourself on, okay, if I run into a situation like this one, remember that the challenge is usually, how do I get this problem started? In this case, seeing this system of equations, knowing that substitution is your best bet, solving the second equation for y, plugging it into the first equation, and not forgetting that once you take the square root of something, you have to remember the plus or minus. I think that's a pretty good overall summary of how you go about solving a system of equations that looks like this. And then have yourself a second index card where on one side of the card you have this system of equations. And then the question that would be associated with it would be, should I use addition or substitution? And what are the first couple of steps? And on the other side of the card, of course, it would say solve using addition. Maybe it would also say to multiply equation 2 by -2, right? So just in order to get the elimination or addition process started. And of course, on that card, also put your reminder to not forget that when you take the square root of something, you get a plus or minus. Are there application problems associated with solving systems of nonlinear equations? There are. And there are too many to possibly cover, and not enough time to go into great detail on enough of them to really make it worth our while. So at least in the course that I'm teaching, which studies this particular topic, we're not going to go into the applied problems. We're just going to stay with the pure math on these. And somewhere down the road, you may end up in a physics class or something like that, where you have, I don't know, maybe there's, you're in the first quadrant and you've got projectile motion happening here, and maybe a bullet is fired or something that's going to be crossing through here, and you want to know at what point in time do the two paths intersect or something. I don't know, I can't even imagine. That could be like a anti-missile system, right? If the curve is the first missile and the straight line is the second thing that's being fired at the missile in order to knock it out of the sky, and you've got to match up the timing, right? You can only imagine the math that's involved to make that happen in three-dimensional space. So this maybe is kind of a gateway topic to a more complicated study of math that's happening in 3 dimensions, right? You can go to the moon with this stuff, literally, I would say. But we'll stop here, and I look forward to seeing you next time. Thanks so much.